Hello and welcome to NPTEL MOOC on electromagnetic waves in guided and wireless media. We will continue the discussion of magnetic vector potential because that, as you will see, is the key for evaluating the fields of an antenna. So, what we have already seen is that we have an equation which is kind of a wave equation, but with a source term for both the electric scalar potential as well as for the magnetic vector potential in the time varying scenario, right. So, if you recall what was that equation, we had this del square A, right, which was very similar to what you had in the case of a wave equation for the electric field, but now for this case you have del square A plus k0 square A, this is in the frequency domain, right. So, in the time domain, of course, this k0 square A actually comes about by having this mu naught epsilon naught del square A by del t square. So, when you take this one into the frequency domain, or rather there will be a minus sign here. So, when you take this into the frequency domain, you are going to get omega square mu naught epsilon naught, which we have labeled it as k0 square. Okay. So, this part of the equation is quite familiar to you. This was the same equation that was satisfied by the electric field component or the magnetic field component in general. So, if the right hand side was actually equal to 0, then we called that equation as a Helmholtz equation, and in fact we use that Helmholtz equation to study the electric fields and magnetic fields of guided structures as well as for other structures. In contrast to that, now what we have is this term which says minus mu naught j. Please note that we are dealing with time varying scenario. Of course, because I am dealing with the frequency domain, I have essentially assumed that the time dependence of every quantity that is there, whether it is the j field or the a field, both will be sinusoidal at the frequency omega. Okay. So, this term is what I have called as source term, and in the absence of source term, we know how the solution of this equation would look like. That would essentially be, depending on the coordinate system, A would be either a plane type of a solution, plane wave type solution, or it could be a cylindrical solution or a spherical wave. So, it would essentially be that. Okay. And because this is the problem of antennas, we are not really interested in dealing with guided structures. We are, in fact, we want to deal with unguided structures or wireless media. That is, there is no connection, physical connection between 2 points where we are considering these type of fields. Of course, if there was such a connection, it would have been a guided structure, but antennas are supposed to radiate into free space or into the air medium, or even in between planets the waves are supposed to be traveling. So, in that case there are no guiding structures, everything is what is called as radiative structure. So, everything is just basically radiation. Okay. And clearly this minus mu naught j that we have included on to the right hand side will simply tell us what is the source of these fields. For example, the current density j will be the source for the A field, the charges will be the source for the electric field, and current density is also of course the source for the magnetic field. And of course, in the case that we are interested, we have let all these quantities be dependent both on time as well as of course on the distance. Okay. I will not go to the formal solution of this equation, that steps are quite complicated and perhaps not necessary for this course, but I will give you a basic solution, or rather I will give you the solution that we normally would have. I mean, at the end of the solution process what we would have. Now, I will switch for a moment back to the time domain. So, basically meaning that I am looking at this equation. Okay. So, I am looking at this equation for a time being, because I will come back to what we are going to do in the frequency domain shortly. Okay. The intuition is first developed in the time domain for now, and then we will use that intuition to see what would be the situation in the frequency domain, and from there onwards we will work with it. Okay. So, in this case what you actually get is this particular equation. I will tell you in detail. So, I will call this as r prime, and please note that it is not a function of time that I am interested in, but what is called as retarded, or a better word would be to call this as delayed time, right. So, v is the velocity of the waves or the potential in the free space, r is the distance from the source onto the observer point. Okay. So, and then divided by 4 pi r and integrated over the volume that the surface current density would actually occupy. So, the basic meaning of this one is, suppose there is a piece of conducting material here which is carrying some current, or equivalently it is carrying a current J, which of course is varying with respect to time as well as with respect to the space. Okay. So, the J is not the same at every point in space, it may be varying slightly, right. And let us say we enclose all of this current in some kind of a volume. Okay. So, that is the volume that I am considering, and let us imagine that I am actually located at this point P, which in general will be given by the position vector r. Okay. So, I am going to assume a coordinate system. From that coordinate system, the position vector onto the point P is given by the vector r. So, OP will be the position vector r. At any point in this volume, the one that I have considered here in general will be represented by a vector which is given by r prime. So, the prime is for the source coordinate, unprimed values are for the field coordinate. Okay. So, at this point I consider this to be a prime, meaning that I am actually considering the source point here, and what I need to know is that how this source would affect the field, or what would be the effect of this source on the field at the point P. Okay. How do we know that? That is by this equation, and then the missing ingredient in that equation is this capital R, which of course in terms of the vector will be given by r minus r prime. Okay. And I am interested only in the magnitude of this, at least in the denominator side, and in the numerator where I am looking at this t minus r by v. I am interested in the magnitude of r, which of course is the vector distance between the source and the observation point. Okay, point where we are observing the field and the source. Now, in the ordinary time invariant scenario, there is no distinction between this source point and the observation point, right, or rather there is a distinction, but there is no time dependence there. What this t minus r by v is telling us is a very simple fact, something that you know from very well, right. So, what this is telling you is that the effect of the current J at this point r prime is actually felt not at the time t, but a time t which is delayed with respect to the observation point, and the delay is given by r by v seconds. Okay. If the waves are propagating with a velocity v, we will not be able to see whatever that is happening at the same instant, but we will be seeing whatever that is happening after a delay of r by v, where r is the distance between our observation and whatever the source is changing, right. So, in the ordinary what is called as non-relativistic velocities, you will not see this change. For example, if your friend is waving at you, right, then you will immediately see that your friend is waving at you, because the distance between you is hardly about a meter or 2 meters, let us say in a typical scenario, right. However, if your friend stands on moon and then waves at you, and you somehow have eyes which you can see on the the person waving on the moon, you will not be immediately seeing. What you would be seeing is how much the distance between earth and moon, that is from the point where you are standing and point where he is standing or she is standing, and then divide that one by the velocity with which light travels, speed of light. Okay. So, that is the minimum time that must be elapsed before his waving of his hands or her hands become apparent to you, right. So, this is a very simple phenomena. For example, the light that we see from the stars are not telling us how the stars would look today, they are telling us how the stars looked at so and so years before. So, for example, if the star is 10 billion light years away from you, it means that whatever the star is the light that you are seeing and you are observing the star's feature is not really happening today, it has happened 10 billion light years ago, and you are simply seeing that one now. So, this is called as the retardation effect or the delayed effect. The source does not immediately be apparent to the observer, the source will become apparent to the observer only after a certain delay, which is r by v seconds has elapsed. Okay. I have of course been calling this as r by v. We know that in the free space, or at least the distances that we are considering on earth, v is basically c, and therefore you can even write the delay as r by c. Okay. I hope that point is very clear. What is happening now here will be observed there, that is observation point, later. Okay. That is the simple meaning of these two equations. Now that we have seen this equation in the time domain, let us now go to the frequency domain. What is the effect of time delay on a cosine wave? The effect of time delay on a cosine wave is simple phase retardation or the phase shift, correct. So, you imagine a sinusoidal signal going all the way from minus infinity to plus infinity. Now, you imagine that wave being delayed by a certain time, right. So, cosine omega t becomes cosine omega of t minus tau, where tau is the delay. So, what you have essentially obtained is this extra factor of omega tau, which would essentially be the delay or the phase shift. This is exactly similar to the start of the course that we considered in the transmission line. Effect of delay on a cosine wave is always a phase shift. Okay. So, we have already seen this thing, and we do remember that if I have a distance r and I know the propagation constant of the wave, then the overall phase shift that I would be seeing would be given by k0 r. Think of your transmission lines, think of your waveguides, whatever that you want to think of, even the uniform plane waves would only tell you this, right. So, the phase delay would be k0 r, and I can convert every quantity in this time domain into the corresponding frequency domain or the phasor domain, and then write A now being function only of r. Please remember that we are working in phasor domain, meaning that we have excited our current source with a frequency of omega, and that is what we are looking for. Okay. So, what you will have is mu 0 by 4 pi, which is a constant, I will pull that out. Then you have j of r prime, and E becomes minus j k r, right, or k 0 r if we wish to still carry around k 0, integrated over the volume where the source is occupied, divided by r, right. So, this is the expression that you are going to get for A in terms of the phasor domain. Now, what is r? We have already seen that r to be magnitude of r minus r prime. Now, magnitude of any vector can be rewritten in terms of its component vectors, right. So, you have two vectors, we will call this as A minus B vectors. So, this difference magnitude can be written as magnitude of A with itself plus magnitude of B with itself minus 2 A dot B under root. Okay. So, for this r and r prime, this would essentially mean that you are dealing with r square plus r prime square minus 2 r dot r prime. Okay. All of this under the root of 2, right. So, this is what you get. Now, we will assume that the source coordinates or the volume that where the source is varying r prime is actually quite small compared to the distances at which we are observing this source. So, think of an element kept in some city which is like say 10 kilometers away or 20 kilometers away, and then you have an AM radio, and then you are listening to this one that is coming from, and so the antenna is essentially very far away from you, and seen from that far away it will almost look like a small point in space, right. And then your observation distance is quite far, that is why it is looking as a very small point, and at that distances any small variations around the source point can be neglected. Okay. So, in fact, this is what we would do when we consider a star. A star, of course, is very big, but we consider star as almost a point particle simply because the distances that are involved, the star appears to be a very small quantity in space, right. So, that is the basic idea out there. So, in that what we essentially mean is that this r prime square, which would represent the magnitude of this r prime vector, right. So, from that, and this is the r vector actually. So, this is the r vector, this is the capital R vector magnitude, and this one is the small r vector prime, right, to the source. So, this length is very small no matter where you take onto the point. So, you can see that this length is very small compared to the observation distance, meaning that this r prime square can be neglected in comparison to r square. Okay. Of course, I can't neglect that in the product because in the product r is there. So, a large quantity minus multiplied by a small quantity will give you a finite value, right. So, that is what we have. So, r I can approximately write this as r square minus 2 r or r prime dot, and I can pull this small r out. Please remember that small r is the position vector of the point P where you are observing the fields. So, if I pull r out, then I will have 1 minus 2 r dot r prime divided by r square under root. Using binomial theorem, I can write this as 1 minus r dot r prime divided by r square. Okay. And because the vector divided by its magnitude will actually give you the unit vector in that particular direction. So, this would be the unit vector r hat in the direction of the vector r. So, I can rearrange this equation and say that r is approximately small r, which is the magnitude of the distance between the origin of the coordinate system and the observation point, minus r hat dot r prime. Okay. So, there are too many r's here, but I hope you are not confused quite confused in all this. The goal here was that I could go back and substitute that into the source equation or the equation for A and write A in a slightly approximate fashion as mu naught by 4 pi r e power minus j k r. Might may seem a little bit puzzling. So, I will first not look at this one and I will go back to this. So, I have this j of r prime, which is essentially the source that would remain, and then you have, sorry, this is k 0, you have e power j k 0 r hat dot r prime. Okay. Why is this e power plus j k 0? Because in r you have a minus sign here. So, I hope this part is fine. Integration over volume is also fine, but in the denominator, instead of writing this as capital R, I wrote this as a small r, and because the integration is not with respect to the volume, I pull this r out and write it out the output. Okay. The reason why I was able to do this, and of course, this is the volume integral, the reason I was able to do this is because in the denominator it does not matter whether you take 1 by r or you take 1 by small r, because as you can see from this picture, these two are essentially equal to each other. The whatever the difference that you have in terms of this length, which is given by this r prime vector, is too small, and in this far field approximation, that is distances very far away from that particular distance that we have considered over the source, the distance from the source point to the observation is the same, almost same as that of the origin of the coordinate system to the point P. Okay. So, with that, this 1 by r can always be approximated as 1 by small r in the denominator, but I can't do that in the numerator, because agreed r prime may be small, but k 0, which is basically inversely proportional to lambda, and lambda could be very small, because these antennas are working for wireless communications in the ranges of 900 megahertz to about 15 or 28 gigahertz, depending on which 3G, 4G or 5G you are working with. So, even in that variation, your wavelength is actually quite small, and because 1 by wavelength is large, lambda is small, but 1 by lambda is large, that can multiply to r dot r hat prime and cause that entire quantity to be almost comparable with respect to this small r. Okay. Therefore, we do not make this approximation in the numerator, but we make this approximation in the denominator. Okay. So, having said that, this is our point now. So, this is where we are now, and we are going to use this equation in order to understand the fields of some simple antenna configurations, and then we will look at some of the important antenna characteristics. Okay. So, our first example would be a very simple antenna element or a radiating element, and that is called as elementary or Hertzian dipole. Okay. So, this dipole, di means two and pole means charges. So, it is an older notation where poles would mean charges. That is why you would have heard terms like poles repel and unlike poles attract. So, the pole word was used in the 18th and 19th century to refer to charges. Now, we do not use them, but it is a convention that has come out. So, dipole means there are two poles, meaning two charges, not of the same kind, they are of the opposite kind, and this dipole essentially would mean that you have a plus charge and a minus charge of equal magnitude, but they are varying with time. Okay. And the distance between these two charges is almost 0. In fact, it for the case that we are considering, the distance is taken to be very, very small compared to the wavelength. Okay. There is a very important aspect as to why we do that. Okay. So, I will assume that this is the dipole that I am considering, whose length is dz prime, and it is a very, very small quantity. Okay. So, this is what I have. So, mathematically I could of course represent this j vector, which is flowing around this one, and it is directed along the z axis. Okay. This is my coordinate system, this is the z axis where I have put the antenna up there, and you have this usual y and x axis, but because you are thinking of radiating fields, it is better to work in the spherical coordinate system. So, before you continue further, I would suggest that you go back and look at your spherical coordinate systems, and you can actually follow most of the arguments that we are going to make from the from this time onwards, provided you are familiar with the spherical coordinate system. So, in the spherical coordinate system you have r, which would tell you the point distance away from the origin, and then you have this theta, and then you project it, you are going to get a distance or the angle measured along the x axis, sorry, this is the x axis, and that would be the phi component. So, this point could be represented by r, theta and phi, and there are some relationships between them which you can easily find out in a mathematical handbook or a formula book. I would suggest that you go and read all of that before you continue with this example. Okay. So, coming back to our example, we are considering an elementary or a Hertzian dipole. I will call this as elementary dipole because this is one of the simplest configurations that you can think of, okay, where the j vector is essentially having some magnitude which we will call as jz0, but it is essentially a vector or essentially a delta function, and this delta function is actually in the space, right. So, you have seen delta functions in time which would be written as delta of t. Now, with delta of r minus r prime would represent that this is actually located at the origin. Okay. So, this can be expanded of course as writing as delta of z minus z naught, z prime del of x minus x prime, and delta of y minus y prime. Okay. So, essentially meaning that it is a very small quantity, so do not worry too much about it, and the current density is I jz0, the current itself can be thought of as I dz prime, which is very slowly varying. Okay. Now, what am I interested in? Of course, I am interested in the observation of the electric fields and the magnetic fields. Of course, the first step for that would be to find out the magnetic vector potential. I am interested in looking at at this point what the fields are. So, I will label the point as P and then draw from the origin a length or a vector which we would call as the r vector. Okay. So, that is the r vector that I have, and you can clearly see that I have this r vector and I have this I have this j which is directed along the z axis, right. So, I have this j directed along the z axis which is given by I dz prime times z hat. So, what would the A field be? A field will be z directed. Why? Because j is along z, A will also be along z. That is the key point here. If it was directly the magnetic field that you were trying to calculate, then the magnetic field would be actually perpendicular to the direction of both j, that is the current, as well as to the plane that joins the observation point to this source, right, and therefore, the direction would also keep changing as you keep moving the observation point all over the place. So, calculation of the magnetic field is slightly more complicated, in fact, it is very complicated. The straightforward way to calculate the magnetic field and the electric fields associated with this radiation element is to calculate A, which will point in the same direction as the j vector, and from A calculate it using the formulas that we have already developed in the last module. Okay. So, A will be directed along z. So, essentially I can rewrite, instead of a vector I can write this as a scalar and have this A z component. So, at this observation point A will be directed along the z component, but please remember I am not interested in looking at the z component, I am interested in looking at the r component as well as the theta component. Remember, this is the theta component, and I want to find out what so of course, this is your angle theta. I want to express now A z in terms of A r and A theta. Okay. So, this conversion from one coordinate system to the other coordinate system in this case is necessary because I want to specify what would happen to my electric fields and magnetic fields or to my A field as I move around the antenna in a particular manner. So, I will be varying r, I will be varying theta, and then I will be varying the phi direction. So, I am moving on points of a sphere of constant radius, or rather radius which keeps on changing, and angle theta which keeps on changing, and phi which is also changing. Okay. So, it is better that we express this A z in terms of A r and A theta. Now, even before I go to this A r and A theta, you may ask, what about A phi? Well, A phi will not exist simply because, see, you have this antenna in this, or rather the element in this manner, right. This is the z directed field. Now, imagine that you are sitting on a ship and then moving around this antenna element in a circle, okay, a very small ship, and then you are moving around the circle. So, as you move away, do you see any change in the current? You do not see any change in the current, it would essentially remain the same, it is uniformly distributed. Therefore, moving around in the circles will not change anything. So, there is no A phi component. So, luckily what we have is only Az, which we will have in terms of Ar and A theta. What is Ar? Ar will be Az cos theta, and then A theta will be minus Az sin theta. Okay. So, these will be the components that you are going to have. So, now that you have this component, but what is Az? Az is basically mu naught by 4 pi r e power minus j k 0 r. Remember, this is the part that we have already done it, and the integration was over the current element, which instead of the volume, it is essentially the current element that you are considering, because this element has no width or no changes in the x and y direction, divided by small r, and which, because I assume the current to be uniform, because it is a very small element, I assume I to be the constant on that particular element, and therefore, this integration simply drops out and becomes I dz, which would be the length of this element. So, instead of dz prime, I will take the length to be dz. Any point here I can take it as dz prime. Okay. So, this essentially becomes mu naught by 4 pi r. Sorry, I have already pulled r out here. So, this is nothing here. So, the equation would essentially be this fellow, right. So, e power minus j k 0 r I dz. Okay. So, this fellow is I dz e to the power minus j k 0 r. So, this is your Az that you have. Okay. Now that you have this Az, right, and you know what is this Ar and A theta in terms of Az, we have completed the solution for A, but I am not interested in A, I am interested in H. I know from the defining equations for A that del cross A is equal to B, but B is mu naught H. Okay. Therefore, H is equal to del cross A by mu naught. Okay. Now, again I would suggest that you go to the curl expression in the spherical coordinate system, substitute for del cross A, that is substitute for A and then put del cross A, and just to remind you what that is, this is r hat by r square sin theta, theta hat by r sin theta, and then you have phi hat by r. You will have del by del r, del by del theta, and del by del phi terms, and then you have ar, a theta, and luckily in this case there is no phi component. So, this is actually r a theta, and this will give you del cross A. Okay. You simply divide this one by mu naught. So, you divide everywhere by 1 by mu naught, and the determinant of this will give you the magnetic field H. Okay. I will not derive this one here, this is an exercise that I will leave it to you, but H can be written as some constant k e power minus j k r sin theta and 1 by r square plus j k by r times phi hat. Now, because we are near the end of this module, I will just comment on one particular point. We said there is no phi dependence on A, but why is there a phi dependence on H? Well, in a simple case, you think of a wire, current being carried by the wire, what is the magnetic field directed along? The magnetic field is directed along the phi direction, right. So, therefore, although A is in the same direction as Z, H is directed along the phi direction. Okay. So, I have obtained H by using the equation, Maxwell's equation del cross H by j omega epsilon naught. You can also find out what would be the electric field E, and you can find out the expression. We will start from these expressions of H and E in the next class and talk a little bit about what are the general antenna parameters. Thank you very much.